In this module, we will be learning about the coordination compounds. Coordination compounds are a special class of compounds in which the metal atoms or ions are bound to a number of anions or neutral molecules. Coordination compounds are a type of addition compounds. When two or more stable compounds are allowed to combine in stoichiometric ratios, crystalline compounds are formed. These are known as addition or molecular compounds. For example, when saturated solutions of potassium sulfate and aluminium sulfate are mixed and heated till the crystallization point is reached, we get the well-known compound potash alum. Similarly, if we add a solution of potassium cyanide to a white precipitate of nickel cyanide, the precipitate immediately dissolves and a red-orange solution of a new compound is obtained. On the basis of their nature, addition or molecular compounds are divided into two categories. They are double salts and coordination or complex compounds. Double salts are molecular compounds that are stable in the solid state. But break down into individual constituents when dissolved in water. Note that the individual properties of the constituents are not lost in these compounds. For example, an aqueous solution of potash alum will give the tests for K+, Al+3 and SO4-2 ions. Other common examples of this class include carnallite and Mohr's salt. On the other hand, coordination compounds are molecular compounds that retain their identity even when dissolved in water. Note that the individual properties of the constituents are lost in these compounds. For example, when potassium ferrocyanide is dissolved in water, it does not give the usual tests for Fe+2 and Cn- ions, indicating that the ion FeCN6-4 does not dissociate into Fe+2 and Cn- ion. Other familiar examples for nickel, copper, and silver are shown here. Actually, these ions are present in the form of a new ion called a complex ion. Compounds that have complex ions are called complex compounds. As the central metal ion in the complex ion forms dative or coordinate covalent bonds with the species surrounding it. Complex ions are also known as coordinate ions, and hence the corresponding compounds as coordinate compounds. Transition metals show a greater tendency to form complex compounds. This is due to the relatively smaller size of the metal ions, higher ionic charges, and the availability of the vacant d orbitals for bond formation. Coordination compounds form the backbone of modern inorganic and bioinorganic chemistry and chemical industry. Naturally occurring complex compounds are vital to living organisms. For example, chlorophyll is a coordination complex of magnesium. Hemoglobin is a coordinate complex of iron, while vitamin B12 is a coordination complex of cobalt. Complex compounds find extensive use in electroplating, metallurgical processes, textile dyeing, and medicinal chemistry. Apart from that, they also find applications as industrial catalysts and analytical reagents. In this module, we will be studying about the Werner's theory. Have you ever wondered how come a stable salt, such as cobalt trichloride, combines with a group of stable, independently existing molecules, such as ammonia, to form new compounds like COCl3 6NH3, COCl3 5NH3, and COCl3 4NH3 with entirely new properties? Alfred Werner, a Swiss chemist, after preparing thousands of new compounds and studying their properties, put forward a theory to explain the formation of complex compounds. It was the first successful explanation for the phenomenon. The theory became famous as the coordination theory of complex compounds, which is also known as Werner's theory. His explanation of complex formation is based on some postulates. The first postulate is that the central metal atom or ion in a coordination compound exhibits two types of valencies, primary and secondary. While writing the structure of the metal complexes, the ligands that are linked by primary valency are shown by dotted lines, while those linked by a secondary valency are shown by thick lines. If a ligand satisfies both the valencies, then it is shown by a thick as well as by a dotted line, and it is said to exhibit dual character. The second postulate states that primary valencies are ionizable and correspond to the number of charges on the complex ion. Primary valencies apply equally well to simple salts and to complexes, and are satisfied by negative ions. For example, the primary valency of 2 in CuCl2 is satisfied by 2 chloride ions. Similarly, the primary valency of 3 in the complex CONH36Cl3 is satisfied by 3 chloride ions. In modern terminology, the primary valency corresponds to the oxidation number. The third postulate states that secondary valencies correspond to the valencies that a metal atom or ion exercises towards neutral molecules or negative ions in the formation of its complex ions. Every metal has a fixed number of secondary valencies or coordination number. For example, cobalt 3+, platinum 4+, and iron 3+ ions are recognized to have a coordination number of 6. Similarly, nickel 2+, copper 2+, and platinum 2+ ions have a coordination number of 4. Secondary valencies are non-ionizable. They are satisfied by neutral molecules or negative ions. The secondary valency is equal to the coordination number of the metal. For example, in the complex COCl36NH3, the 3 chlorides are held by primary valencies, and the 6 ammonia ligands are held by secondary valencies. The fourth postulate states that secondary valencies are directional, and so a complex has a particular shape. The number and arrangement of ligands in space determines the stereochemistry of a complex. The most common coordination in transition metal complexes is 6, and the shape is usually octahedral. The coordination number 4 is also common, and this gives rise to either tetrahedral or square planar complexes. This postulate predicted the existence of isomerism in coordination compounds. To distinguish between the two types of valencies, Werner introduced the concept of using square brackets to enclose the atoms that make up a coordination complex and which are therefore not ionized. The postulates of Werner's coordination theory were actually based on experimental evidence rather than theoretical. Werner treated cold solutions of a series of compounds of cobalt 3 chloride with ammonia with an excess of silver nitrate and weight of the silver chloride precipitated. The stoichiometries of the complex silver chloride formed were as shown here. Werner deduced that in COCl3 the primary valency or oxidation state of +3 is satisfied by 3 chloride ions. The coordination number of cobalt 3+ ion is 6. As there are 6 ammonia molecules in the compound, they alone satisfy the 6 secondary valencies of cobalt. As you can see, the primary valencies are represented by dotted lines and the secondary valencies by thick lines. In modern terms, the complex is written as CONH3 6Cl3. The 3 chloride ions are ionic and hence are precipitated as silver chloride by silver nitrate. Thus, the complex will ionize in solution and give 4 ions. That is, 1 CuNH3, 6 3 plus ion, and 3 chloride ions. Werner deduced that the loss of one ammonia molecule from COCl3 6NH3 should give COCl3 5NH3. This complex has only 5 ammonia molecules. Therefore, to satisfy the coordination number of 6 of cobalt, one chloride ion exhibits dual behavior. That is, it satisfies the primary as well as the secondary valency of cobalt. In modern terms, the complex can be written as CONH3 5Cl Cl2. Thus, only 2 of the 3 chloride ions are ionic, and thus only 2 are precipitated as silver chloride with silver nitrate. On ionization, this complex will give 3 ions, 1 CONH3 5Cl2 plus ion and 2 chloride ions. As can be seen from its structure, one chloride ion, which is playing a dual role, is shown by a thick as well as a dotted line. Similarly, in CuCl3 4NH3, to satisfy the secondary valency of 6, 2 chloride ions assume dual behavior. In modern terms, the complex can be written as CONH3 4Cl2Cl. Thus, only one chloride ion can be precipitated as silver chloride. This complex, on ionization, gives 2 ions, one of CONH3 4Cl2 plus and the other of chloride ion. The structure of the complex is shown here. Although Werner's theory successfully explains the bonding features in coordination compounds, it suffers from some drawbacks. It doesn't explain why only certain elements form coordination compounds. It does not explain why the bonds in coordination compounds have directional properties. It does not explain the color and the magnetic and optical properties of complexes. In this module, we will be studying about the nomenclature of the coordination compounds. The names and formulae of coordination compounds are written by employing the rules published by the International Union of Pure and Applied Chemistry, or IUPAC in short. Let's look at the rules framed by IUPAC for writing the formula of a complex. The first rule is the formula of the cation, whether it is simple or complex, is written first, followed by that of the anion. For example, in the complex shown here, the cation sodium is written first, followed by the anionic coordination entity. Similarly, in the complex containing a complex cation and a complex anion shown here, the complex cation AgNH3 2 is written first, followed by the complex anion AgCN2 The second rule is that within the coordination sphere, the symbol of the central atom is written first, followed by the symbols or formulas for the ligands in alphabetical order, irrespective of the charge on them. For example, in the complex shown here, the metal atom cobalt is written first, followed by the ligands ammonia and chloride. Polydentate ligands are also listed alphabetically. While listing in alphabetical order, the first letter of the abbreviation of the ligands is used to determine their position. For example, if a complex contains chloride and ethane 1,2-diamine, which is abbreviated as EN, then in alphabetical order, chloride is written first, followed by ethane 1,2-diamine. Another rule is that the formula for the entire coordination sphere is enclosed in square brackets. For example, in the complex shown here, the coordination sphere containing the metal atom copper with 4 bromine atoms are enclosed in square brackets. The cation potassium is written outside the coordination sphere. The formulae for polyatomic ligands and the abbreviations used for the ligands are enclosed in brackets. For example, EN, EDTA, PY, etc. are enclosed in brackets. For example, in the complex of cobalt shown here, the coordination entity contains the polyatomic ammonia ligand and the abbreviated ethane 1,2-diamine ligand enclosed in brackets. One more rule is, within a coordination sphere, the metal atoms as well as the ligands are listed without any space between them. For example, in the complex of cobalt shown here, the ligands ammonia, water, and chloride are listed without any space between them. Yet another rule is that when the formula for a cationic or anionic coordination sphere is to be written without that of the counter ion, then the charge with the number before the sign is written as a right superscript outside square brackets. For example, the complex ions of cobalt and chromium with the charge on the respective ions are shown here. Now let's see the IUPAC recommendations for writing the names of complexes. The first rule is, for coordination compounds that are ionic, that is, the coordination sphere serves either as the cation or the anion of the ionic substance, the cation is named first and separated by a space from the anion. For example, in the complex K4FeCN6, where the coordination sphere is an anion, the cation potassium is named first and separated by a space from the name of the anion. On the other hand, in a complex such as CONH3, 6Cl3, where the coordination sphere is a cation, the cationic coordination sphere is named first, followed by the name of the counter anion, chloride. The second rule is, while naming the coordination sphere, ligands are named first, followed by the name of the central metal atom or ion, with its oxidation state in Roman numerals in parentheses. Remember that irrespective of the charge on the ligands, they are named in alphabetical order. For example, in the complex PTNH3, 2Cl4, the ammonia ligands are named before the chloride ligands according to the alphabetical order, followed by the name of the metal ion with its oxidation number enclosed in brackets. IUPAC has also proposed certain rules for naming ligands. Anionic ligands are given names that end in the letter O. When the name of the free uncoordinated anion ends in ate, the name of the ligand is changed to end into ato. For example, the anion acetate is named acetate, sulfate as sulfato, thiocyanate as thiocinato, and carbonate as carbonato. When the names of the free uncoordinated anions ends in "ide", the ligand name is changed to end in "ido". For example, the anion fluoride is named fluoride, chloride as chlorido, bromide as bromido, and iodide as iodido. Similarly, nitride is named as nitrido, amide as amido, and azide as azido. Neutral ligands are given the same name as the uncoordinated molecule. For example, pyridine, dinitrogen, dioxygen, and triphenylphosphine. However, some neutral ligands are given special names. They are aqua for water, amine for ammonia, nitrosyl for nitric oxide, and carbonyl for carbon monoxide. Positive ligands such as nitronium, hydrazinium, and nitrosonium are named as such without any change. Another rule says if several ligands of the same type are attached to the central metal atom, then their number is indicated by the prefixes di, tri, tetra, penta, etc. For example, in the complex CONH3, 3H2OCl2, the 3-amine and 2-chlorido ligands are indicated by the prefixes tri and di, respectively. However, if the name of the ligand in question already includes a numerical prefix, then the prefixes like bis, tris, tetrakis, and pentakis are used. For example, the complex RuCl3, PPH3 is named as tris triphenylphosphine trichloridoeuthenium 3. Here's another rule. When the coordination entity is either neutral or cationic, the usual name of the metal is used. For example, the neutral complex shown here is named triamine trichlorido-cobalt 3. Similarly, the cationic complex CrH2O 4Cl2Cn is named tetra-aqua dichloridochromium 3 chloride. Note that in either case, the usual name of the metal is retained. However, when the coordination entity is an anion, the name of the metal ends with the suffix "ate". For example, the anionic complex NAPT-NH3O3Cl3 is named as sodium triamine trichlorido-plutonate 2. For some metals, such as iron, copper, silver, and gold, their Latin names ferrate, cuprate, argentate, and orate are used. For example, the complex K2COCl4 is named potassium tetrachloridocuprate 2. Similarly, the complex NaAgCN2 is named as sodium dicyanoargentate 1. In this module, we will be studying about the crystal field theory. The theory was proposed by Hans Bethe and Van Vleck. This theory gives a much more satisfactory explanation for the bonding and the properties of complexes than the valence bond theory. The crystal field theory is based on certain assumptions. The interaction between the metal ion and the ligand is purely electrostatic. That is, the metal-ligand bonds are 100% ionic in nature. Negative ligands are treated as point charges, and neutral ligands are treated as dipoles. Thus, the bonding in the complex may be an ion-ion interaction or an ion-dipole interaction. The 5d orbitals in an isolated gaseous metal atom or ion are degenerate. That is, they all have the same energy. However, when the ligands approach the metal ion to form a complex, the electrons in the d orbitals of the metal will be repelled by the negative charge, or lone pair electrons of the ligands, due to the repulsion force between the like charges. As a result, the energy of the d orbitals increases and the degeneracy of the d orbitals is lifted. It results in the splitting of the d orbitals. The pattern of splitting of the d orbitals depends on the number of ligands and their arrangement around the central metal atom or ion. Let's look at the application of the crystal field theory to octahedral complexes. In octahedral complexes, the metal ion is at the center of the octahedral, and the 6 ligands lie at the 6 corners of the octahedron along the 3 axes X, Y, and Z as shown here. The approach of the ligands towards the central metal ion is considered a 2-step process. In the first step, it is assumed that the ligands approach the metal ions spherically, that is, at the same distance from each d orbital. At this stage, the energy of all the d orbitals is raised by the same amount. That is, the 5 d orbitals still remain degenerate. The average value of the energy of the d orbitals at this stage is taken as 0, and this is called the barycenter. However, out of the 5d orbitals, 2, that is, the dx square minus y square and dz square orbitals, which are collectively known as the EG set of orbitals, are oriented along the axes towards the direction of the ligands. Thus, the EG set of orbitals will experience more repulsion and the remaining 3 orbitals, that is, dxy, dxz, and dyz orbitals, which lie in between the axes. These 3d orbitals are collectively known as the T2g set of orbitals. Consequently, the energy of the EG set of orbitals increases, while that of the T2g set decreases, relative to the average energy in the spherical crystal field. Thus, under the influence of the ligands, the degeneracy of the 5d orbitals of the metal ion is lost, and they are split into two groups of different energies. This effect is known as crystal field splitting. The extent of splitting in energies is represented by the symbol delta O. The subscript O indicates octahedral geometry. Due to this splitting, the energy of the two Eg orbitals will increase by 3/5 of delta O, while that of the three T2G orbitals will decrease by 2/5 of delta O. The magnitude of crystal field splitting depends upon the field strength of the ligand and the charge on the metal ion. Ligands that cause only a small degree of crystal field splitting are termed as weak field ligands, while ligands that cause a large splitting are called strong field ligands. In general, the common ligands can be arranged in ascending order of field strength as shown here. The order remains practically constant for different metals, and this series is called the spectrochemical series. It is an experimentally determined series based on the absorption of light by complexes with different ligands. Now let's assign electrons in the d orbitals of the metal ion with d4 configuration in the octahedral coordination entities. Obviously, the first, second, and third electrons occupy the low energy T2G orbitals in accordance with Hans's rule. However, for the fourth electron, there are two possibilities. The first possibility is that it may enter a T2G orbital and pair up with an existing electron there. The other possibility is that it may enter the higher Eg orbitals. The exact path followed by the electron depends on the relative magnitude of the crystal field splitting, delta O, and the energy required for the electron pairing in a single orbital, that is, pairing energy B. If the crystal field splitting energy is less than the pairing energy, then the fourth electron enters one of the higher energy Eg orbitals, giving the configuration T2G3EG1. Ligands for which the crystal field splitting energy is less than the pairing energy are known as weak field ligands. The complexes formed with these ligands would be high-spin complexes. If the crystal field splitting energy is higher than the pairing energy, then the fourth electron enters a T2G orbital and pairs up with one of the electrons, giving the configuration T2G4EG0. Ligands for which the crystal field energy is higher than the pairing energy are known as strong field ligands. The complexes formed with these ligands would be the low-spin complexes. Now, let's look at the crystal field splitting in tetrahedral complexes. The approach of the ligands in a tetrahedral field is as shown in the figure. You can observe from the figure that the ligands interact more with the T2G orbitals than the Eg orbitals lying between the axes. This is because The T2G orbitals are oriented along the direction of the approach of the ligands. Thus, in tetrahedral splitting, the T2G orbitals are of higher energy and the 2EG orbitals are of lower energy. You can see that the d orbital splitting in tetrahedral geometry is exactly the reverse of octahedral splitting. The crystal field splitting in tetrahedral complexes, which is denoted by delta T, is smaller than the octahedral complexes. The difference in energy can be represented by delta T is equal to 4 by 9 times of octahedral splitting. This splitting energy is not large enough to force the electrons to get paired up. Thus, low spin configurations are rarely observed.